But the session is about new processes. I'm going to be talking more about how we can use an existing process route, but optimizing that process route. So as a broad background, the type product specifications are difficult to meet in complex steel microstructures that go through multiple process steps that I'll talk about in a minute. But there are obvious opportunities for product differentiation in the later stage of processing. So there's always this drive, as Louis indicated, about increasing properties. Gave the example there of strength, but the other properties are important. But by and large, these have to be driven through existing plant. Unless there's major new investment, these improvements must be done through the existing plant. So this raises issues about the fundamental metallurgical building blocks. So the first that I list there is austenite conditioning during hot working. This has been around a long time, and there's been relationships between the austenite grain size and the product dimensions, but the austenite interfacial area per unit volume is much more important, and surprisingly that hasn't been explored for many steels. Then, of course, there's the issue about retained austenite and the formation of reversed austenite in many of the steels. I'm going to talk about one where reverted austenite is important. There is always a competition between carbide formation and the formation of reverted austenite, because carbon stabilizes austenite. The partitioning of alloys between the phases is crucial, and of course we always have the effect of segregation on all of these. So this shows the complex process route, not necessarily all bits for all steels, but as I mentioned, the austenite conditioning up here, there's a whole range of issues there about obviously recrystallization of austenite, and indeed whether we roll down into the intercritical region and get strain-induced ferrite, which gives us substantial modifications in microstructure further down. And then, so the austenite area per unit volume has effects clearly on ferrite grain size, but also on martensite start finish temperatures, and indeed the structure of the martensite that is formed. And clearly there's issues about whether there's retained austenite at this stage, and then if the steel is tempered. We have these complex interactions of the solute as it redistributes, the austenite reversion, and carbide formation, which, as I said, is a competing process. And indeed, as I'll show you in a minute, the temperature range for this can be extremely narrow to get the properties that we want. And finally, some steels have a second temper, which is often regarded as a stress relief, but in fact, it has important metallurgical consequences that we'll talk about. So I'm going to go through three examples, and the first of this is on a super 13 chrome martensitic steel. You have the composition there, the chrome level, and the nickel. It has very low carbon, 0.03, but that doesn't mean to say that amount of carbon isn't important. Equally, there is molybdenum there, which, as we'll see, is also important. So these are the typical strength levels. I haven't given here the range that one has to hit, but it is quite narrow. So the complex microstructures that we see, so on the left here, you have an optical micrograph, and I think we'll agree that it's all far too complicated really to differentiate what's going on. The middle image here shows the, just been etched here to show the austenite. So the austenite is the bright. That's reasonably homogeneous distribution of it, but nevertheless we can see it's elongated again along the martensite lath boundaries. And then in the right-hand one here, we have the higher magnification image. You can see the austenite, which are these bright lumps here, but also you can start to see the carbides that are formed on the lath boundaries, which are also important. As I say, they compete with the austenite for carbon partitioning in there to stabilize the austenite. So this shows the complexity of what is going on. So here we're plotting the retained austenite content against the tempering temperature. And the red here is for, the blue is for single tempering and the red is for double tempering. And we get this very sharp peak. So just dwell on this. You look at the temperature range here is only 20 degrees and the big changes, 25 to 40% approximately, in the austenite contents. Very sharp changes in austenite content over very small differences in temperature. Below the peak, then single tempering, double tempering has no effect, but above the peak, then double tempering seems to stabilize the austenite more than the bottom. So the right-hand diagram here is the same retained austenite, but here we've got the Holloman-Jaffe parameter. So we're just including time now as well as temperature within this plot. And again, we see this really sharp peak and this really tight control that we have to perform to get within the properties that we want, which is shown here. So this is a graph on the left is just the one you've seen, but on the right we're showing the proof strength effect over the same temperature range as there, again using the Holloman-Jaffe parameter here. And this shows remarkable changes, so we're up at 800 megapascals thereabouts, going down to a minimum of about 500, and then again above the minimum. There is a difference between the single tempering, which is this, and the double tempering. So really narrow range of temperature in which quite substantial changes in proof strength are resulting. The question is, why is this so sharp? Why do we get such critical behavior in this way? So just looking at the two steels, selecting here just to give a range. So one has 16% austenite, the other 28% austenite, giving a range of proof strength 786, 670, which is quite significant. Looking at the microstructures, this is the lower strength, higher austenite in the TEM. It's a complicated structure. It's difficult to describe. You can see the martensitic matrix in the background here. The darker regions here are the austenite, which appear bright in the annular dark field image. We can simplify that down somewhat by looking at the phase distribution. So this is pretty much the same area we just looked at. In the right-hand image here, the blue is the ferrite, or the tempered martensite, I should say, and the red is the austenite. You can really quantify the distribution of austenite quite nicely. The middle image is showing the local orientation, so from this we can start to get some idea of the microstructural scale, the grain size, and so on. The EDS maps at the bottom are showing the distribution of nickel, as you would expect, is partitioned into the austenite. The manganese, actually, if you look at it carefully, there is some partitioning of manganese into the austenite. I'll come back to that in a minute. And here, the molybdenum is showing up as the carbides that are formed, as I say, 0.03. Carbon is very low, but nevertheless, carbides are there and play an important part. If we look now at the lower austenite content steel with a higher yield strength, we see that microstructure looks pretty similar. Clearly there's lower austenite, we can quantify that, but otherwise we would be very hard put to see any particular difference that's going on in this case. Now, I mentioned manganese, and I think one has to be very careful about the distribution of manganese and understanding local segregation. This is just giving one example here, where you get austenite, martensite in the TM image. Really difficult to understand what's going on there. When you look at the manganese map, which you can see here, you can see manganese is partitioning the carbides, but also there's this interesting little region of manganese partitioning between a region of austenite and tempered martensite. Another example here, these just little lines here. So subtle effects, but we believe quite important. So a lot is going on, and this just summarizes what's going on within the chemical composition changes. So we're looking here at the temperature range that we saw this very sharp peak in. The chromium stays approximately constant, the molybdenum equally so, but that's hardly surprising given it's in the carbide. But there's quite a change in the nickel content as it goes through here, as you go up to higher temperatures. So nickel is moving around, other elements are not, but the other is carbon, of course. And there's a very dramatic change as you go across these relatively small temperature ranges in the carbon content in the austenite. So that is partitioning around, set in single temper. But once you've done that temper on the second temper, then the carbon actually remains constant. So there's some interesting metallurgical consequences between those. So that's the first where I hope I've illustrated how complicated the microstructures are and the subtle differences that are going on that have very unsubtle effects on the mechanical properties. I'm going to briefly go through two other case studies here. This one is with British Tata Steel, and this was looking specifically at developing high-strength steel that could be used on existing strip line, and this is for these regions here on front chassis frame that required high yield strength, high tensile strength, but you needed also good bendability, so a combination of formability, both in bending and straight ductility, as well as high strength, which are really rather difficult to achieve. And this had to be done on the existing product line, which you can see here. So within the hot rolling temperature range, and then controlled cooling into the coiling range, and then very careful control of that coiling temperature to achieve the final product properties that we wished. This range, again, given us 600 to 650, sounds quite broad. But as with the previous case study, even 5 degrees centigrade change in that temperature had quite dramatic effects on the properties. So the microstructures we get from this are really rather beautiful. We get a relatively fine grain size in a largely ferritic matrix. Grain size typically of about 2 microns here. The key to this is developing a very fine precipitation of vanadium carbides in this case. It can also be done with titanium carbides. You can see just about within these images the very fine distribution of the carbides aligned in these beautiful lines showing interphase precipitation. They are extraordinarily fine if you get the process conditions correct. You can see here the high resolution image. Sorry, the scale bar is missed off here, but you can see the lattice lines, and so they are just in the region of 1 to 3 nanometers in size, extraordinarily fine. And we can only truly see those when we look at atom probe studies, and we can see now the very high number density of extraordinarily fine precipitates. And as the graph on the right shows, and these can contribute up to 500 megapascals of yield strength. So quite a massive contributor to achieving high strength. As I say, using existing product line, but controlling that process extremely carefully. Oops, too far. Right, and the third is a bit left field. This is looking at a case where we had an idea about increasing copper content in steel, that we all know about residuals as they increase. So we had somebody in my group who decided just to dump a very large amount of copper in, about 4% in this case, and see what happens. I thought he was mad, but actually he pulled off quite an interesting observation. So here, I won't go through the process conditions for this steel, but it was processed in such a way that recrystallization was induced, and normally, as that is heated, then grain growth occurs very rapidly. But in this case, we induced a very large number density of very fine copper precipitates. I sort of hesitate to call them precipitates because they're just regions of copper segregation, really. And those were just occurring at exactly the right time that they pinned the boundaries as they started to grow. And that retained this extraordinarily fine grain size, averaging about 500 nanometers. You can see here the atom probe showing the distribution of the copper, a massively high number density of these fine precipitates, want of a better word, and then the high resolution image on the side. You can see there 2-3 nanometers again. They are almost continuous change in copper between the interprecipitate regions and the precipitates themselves, which gives just occurring perfectly at the right time to stop the the recrystallization process. And when we get the look at the tensile strength properties, then we can achieve a yield here of 713 megapascals. That's dramatic work hardening range as we get up to a UTS of just short of 2 gigapascals with a true strain here of 0.45. So extraordinary ductility properties. And if we then plot the yield strength on there and the product of the strength and elongation on the vertical axis, and there's all the different steels that people produced. They come outside the sort of classic banana diagram. Now, interestingly, the copper precipitates are not really strengthening the steel, but they are just stabilizing that extraordinarily fine grain size that we achieved. So that's 3 case studies, and I think just to bring those to a conclusion. So I think I've shown you that there's a substantial scope for the improvement of properties through process control, very fine process control. And although we've had control rolling low alloy steels for some time, there is still much scope in understanding the role of austenite conditioning and optimizing that for a wide range of steel compositions. But we have to understand the role of alloy partitioning on the microstructure because the interactions are really rather complicated. And I think we're still some way off knowing exactly how to control this. Okay, I should just acknowledge a load of other people that contributed to this work, other than those that appeared in the title. So I should acknowledge EPSRC grant as well as Sustain, the work at Tata Steel with Liberty Steel, and then a range of collaborators both at Sheffield and around the world. Okay, that's me.